So before we can talk about the dissociation of water, I want to revisit the concept of equilibrium that I very briefly introduced in the first part of this lesson. Okay, so a reversible reaction can occur in either direction. So what does that mean? Well, you will often notice that for a reversible reaction, we write two arrows. One that points towards the products, which is what you're probably used to seeing. But then there's another arrow that points towards the reactants. What does this mean? Well, it means that, as we have understood in the past, reactants, here carbon monoxide and water, can react together to form these products. But once you have enough products formed, those products can then react with each other to then form back the reactants. And this is what we mean by a reversible reaction. Not only can it go in the forward direction, meaning not only can it make products, but the products can also react with each other to go back in the reverse direction to make reactants. So when a system is at equilibrium, this means that the rate of the forward reaction, meaning the rate at which you are making products, is equal to the rate at which you are making reactants. So when you reach this state, the net concentrations of either reactants or products are not going to change. However, you are still having reactants being converted to products still being converted to reactants. It's just that since the rate is the same, you will not see a change in the net concentrations of either. Okay, so what can we do with that concept? Okay, well, we can generate an equilibrium constant. Okay, so once your reaction is at equilibrium, meaning the rate forward is equal to the rate in the reverse direction, we can write this constant. Okay? And this is how we wrote the acid dissociation constant. Recall that here, our equilibrium constant is capital K. Okay? And we define this as the concentration of products in moles over liters, or molarity. That concentration divided by the concentration of each reactant, okay, also in molarity. Okay, so we have products and we have that divided by reactants. So here, our capital K is our equilibrium constant. Our capital letters are going to be our compounds, and the superscripts here are going to be the coefficients. So I'm going to show you an example here. So let's say you have this reaction, nitrogen and oxygen, and they combine to make nitrogen monoxide. Okay. Well, first I recognize that there's a double arrow here. This is letting me know that this is actually a reversible reaction. And because it's a reversible reaction, I can write an equilibrium constant. That constant is down here, it's capital K, and that is just products over reactants. So I can look at my products and I write an O concentration. That's why I'm using the brackets. Those brackets mean concentration. And then my superscript is going to be the coefficient in my reaction. So I'm done with products. Then I do that over reactants. I can put the concentration of each one. That's why the square brackets are there. And that is the expression for your equilibrium constant. Let's compare that with the dissociation of water. So first, let's recall that water can behave as both a Bronsted-Lowry acid and a base. Okay, we call this an amphoteric compound. Okay, so what this means is that if you have a beaker of just pure water sitting on your tabletop, this means that one water molecule can act as an acid, another water molecule can act as a base, and they can therefore react as an acid-base reaction. Okay? And that's what's being shown here. So you can see here we have our water acting as an acid, another water molecule, H2O, acting as a base. Okay? So this water molecule is going to donate its proton, and this water molecule on the right-hand side is going to accept it. Okay? So when the acid donates its proton, it becomes a hydroxide ion. Okay. And when the water acting as a base accepts it, it becomes a hydronium ion. So basically what this means is that water molecules can dissociate into ions. Specifically, they dissociate into OH- and H3O+ ions. Okay. But now let's look at these arrows here. This is a reversible reaction. There are two arrows, one pointing towards products, one pointing towards reactants. But what you'll notice is that the top arrow pointing towards the products is very small. And this is because water dissociates to a very small extent, meaning that most of the water in your beaker is in H2O. Okay, it is like this. But just a very small fraction is going to react with each other to form your ions, to form the hydroxide and the hydronium ions. How small is that amount? It's actually very small because we can measure it. So that amount at 25 degrees Celsius is going to be 1 times 10 to the negative 7 molar hydroxide ions. And then you're also going to have 1 times 10 to the negative 7 molar hydronium ions. Okay, so it's a very, very, very small amount, but it's enough for it to be measured. So now what does this mean for its dissociation constant? Okay, so from the reaction of two water molecules, we can write an equilibrium constant like we did for the acids. So the first thing we do is write our capital K, and then we write our products over our reactants. Okay, so our products in a water dissociation, when water dissociates, it's going to form your hydronium and hydroxide ions, and then your reactants are going to be two water molecules. So because we have two water molecules here, we can go ahead and write a 2 as a superscript. All right, now we're going to do just as we did with the acid dissociation constant. We're going to multiply both sides by water because the concentration of water isn't really changing, of H2O. It's not really changing very much. It's not significant. So we'll take it over to the other side, and that is what helps us arrive here, where now we have Kw. Notice this W here is for water. That's what's different with Ka. Ka is specific to acid dissociation. This one is going to be specific to water dissociation. So sometimes you'll see this constant called the water dissociation constant. Other times you might see it called as the ion product constant. Okay. So how is this useful to us? How can we use this? All right. So we arrived in the previous slide. We were able to show that we can write an equilibrium constant for water that is equal to hydronium times hydroxide concentration. So I have rewritten that up here. So it turns out that since we can measure the hydronium and hydroxide ion concentrations, which are these values here, we can plug that in. So I plugged that into H3O plus and OH minus. And then when you multiply those two together, you get this value here. So it turns out that Kw is actually a constant, and it equals 1.0 times 10 to the negative 14 molar squared. And this is going to be true for all aqueous solutions at 25 degrees Celsius. Okay? So we're actually going to be able to use this equality to determine the concentrations of hydronium or hydroxide ions in the solution. And we can use that by setting Kw equal to its constant. And I'm just plugging that in here. Oops. Plugging it in there. Okay. So that's what I've written here. 1 times 10 to the negative 14 molar squared is just my Kw value. And then that equals the concentrations of each one. Okay, all right. So what does this all mean in terms of acidity and basicity and neutrality? So we use the dissociation of water as our reference point for neutral. Okay, so the natural dissociation of water, which is 10 to the minus 7 H3O plus and 10 to the minus 7 molar OH minus, that is naturally how much of each one you're going to have, or what concentration of each one you would have in just a cup of water. Okay, we consider those concentrations as neutral. Okay. Now, what do we mean by acidic? So recall that an acid donates a proton to water. And when we do that, so if I have a cup of water and I add acid to it, that acid is going to donate a proton to that water. And that is going to form more H3O plus ions. So there were already some H3O plus ions that existed in just water, which is exactly this. Okay. Now I've added acid to that water, so I'm increasing the amount of H3O plus in there because my acid is going to donate that proton to water to form H3O plus or hydronium. Therefore, acids increase that hydronium concentration when you add them to water. And this is what we call an acidic solution. All right. So an acidic solution is characterized by more H3O plus ions or hydronium ions than hydroxide ions. Base is going to be the reverse. When you add a base to water, it's going to accept hydrogens from water, and that is going to form hydroxide ion. So what that means is that when you dissolve a base in water, you're increasing the amount of OH minuses in there. Okay, and this is what we call a basic. So you'll notice that when we increase hydroxide ions, we simultaneously decrease the amount of hydronium. Okay, So it's a bit of a teeter-totter type of situation where if you increase H3O plus, that will decrease your OH minuses. Okay. So again, it's characterized if you have more H3O plus than OH minus, that's acidic. If you have more OH minus than H3O plus, then you're basic. All right, let's put everything to practice. All right, so here we're going to calculate the value of hydronium concentration or hydroxide concentration from the given values. And then we're going to label the solution as acidic or basic. So in A, I have a cup of coffee, and they have given me the OH minus concentration. They want me to calculate H3O plus concentration. So what this means is that for both of these problems, I can use the expression of Kw that we just talked about, which is just the hydroxide ions multiplied by the concentration of hydronium ions. Okay, and we determined and we derived, and I showed you that that equals 1 times 10 to the negative 14 molar squared. Okay. So this is the equation we're going to be using. And again, this comes from the natural dissociation of water. Okay. So let's start with A. Okay, so since I'm using this equation, I'm going to go ahead and plug in my Kw, which is 1 times 10 to the negative 14 molarity squared. That is going to equal my OH minus concentration. So I will put 1.1 times 10 to the negative 9 molar. And then I am solving for H3O plus. So I can go ahead and solve for H3O plus. In order to do that, I'm going to divide both sides by 1.9 times 10 to the negative 9 molar so that these will cancel. And then I will do the same here. Okay. Here, the unit that squared is going to cancel with this 1 molarity, leaving me with just 1 m. All right, so when you plug that into your calculator, what you will get is 0.909 times 10 to the negative 5 molar. Okay. But we're going to notice that we can only have 2 significant digits here. So that means 1 and 2. This is the last digit I can have. So I'm going to look at its neighbor. If it's greater or equal to 5, then I have to round this number up. It is a 9, so I do need to round up the 0. So I will round it up to a 1. This will be times 10 to the negative 5 molar. So this is how many H3O plus concentrations I have. Okay. As I canceled these and I solved for H3O plus. So what does this tell me? Well, I can see that my H3O plus concentration, H3O plus, is greater than this H3O plus concentration, which is 0.91 times 10 to the negative 5. That concentration is actually greater than the concentration of OH minuses. This actually should be turned into proper scientific notation, which is 9.1 times 10 to the negative 6 molarity. This is the correct answer. So my hydronium ions are going to be greater than my hydroxide ion, which is 1.1 times 10 to the negative 9. Okay. So what this means is that we have an acidic solution. This is going to be acidic. Because my H3O plus ions are at a higher concentration than my OH minus. Okay. Let's do another example, B. Here they have given me H3O plus concentrations. So I'm going to go ahead and use the same Kw equals to hydronium times hydroxide concentrations. So I will just do this. And I know this is equal to H3O plus times OH minus. Okay. Let me just erase those lines. Okay. All right, so now I solve for OH minus. I need to divide both sides by 5.0 times 10 to the negative 7. So let's just go ahead and write that in. Okay, that way these cancel and I'm left with just hydroxide. Over here, I will do the same. Okay. Now this will cancel with that. And so I am left with OH minus is equal to, you're going to divide those two together, and you will find that that is 2.0 times 10 to the minus 8 molar. And that's the concentration of my hydroxide ion to the proper number of significant digits. Okay, so what does this mean? Well, H3O plus concentration is 5.0 times 10 to the negative 7. My hydroxide concentration is 2.0 times 10 to the negative 8. So 10 to the negative 8 is smaller than 10 to the negative 7. So this means that H3O plus is in greater concentration than OH minus. So if I look at my chart, whenever H3O plus is greater, that means we have an acidic solution. Okay, so that is how we calculate hydronium and hydroxide ions in a solution using the water dissociation constant, or Kw. Okay? So we can find concentrations of each ion. Now we're going to use the concentration of the hydronium ion, H3O plus, to define pH. And pH is going to be an easier way for us to determine whether something is acidic or basic. Okay, so this is our equation of pH. You're going to notice that pH equals the negative log of the hydronium ion concentration. Okay, so if you were to plug into here, the hydronium ion concentration of water, just pure water, which we said was equal to 1 times 10 to the negative 7 molar. This is the concentration of just hydronium. So when water naturally dissociates, that is the amount of hydronium ions it would generate naturally. So if you plug that in there and you plug that into your calculator, what you will notice is that when we plug that in, you are going to get a value of 7. Okay, and this is why a neutral solution is going to have a pH that's equal to 7. Because when we plug in the concentration of H3O plus, naturally, of water, you're going to get a pH of 7. So when the pH is 7, this is a neutral solution. Okay? Now, if we plug in a concentration that is greater than 1 times 10 to the negative 7, and meaning we have more hydronium ions in our solution, that is going to produce a pH value that is less than 7. And when it is less than 7, we call this acidic. It's acidic because we have an excess of hydronium ions. Now, the basic is the opposite. When we have a very low amount of hydronium ions, meaning it is less than that of neutral water, okay, when we plug those values into that equation, we're going to find that the pH value is going to be greater than 7. Okay, so when the value is greater than 7, we call this a basic solution, okay, because it has very few hydronium ions, meaning it has an excess of hydroxide ions, or OH minus ions. Sometimes we will be given the amount of hydronium ions to plug in, but sometimes we're going to be given the pH value, okay? So we can plug in our pH value and then solve for H3O plus, which is what I have done here in this bottom equation here, okay? So when you are given a pH value, you can just use this bottom equation in order to calculate the hydronium ion, okay? And if you're given the hydronium ion concentration, you can plug it into the first one to calculate pH, and we'll do a few examples of that. Okay, so here's our pH scale. Here in the center, we have neutral, because pH equal to 7 is neutral. Any pH that is greater than 7 is going to be basic. So you can see all these household products, many of them are cleaning products. They're going to be more towards the basic. Okay, you're going to see milk is close to neutral. And then these fruits, which contain acids, they are going to be more acidic. Their pH is going to be lower than 7. So a smaller pH value means a more acidic solution. These things down here, this is a pH meter. This is one way we measure in the lab the pH of a solution with good accuracy. And this here is going to be a pH strip. You're going to be using these in the labs that you will be doing this semester. And how these are used is you place a little dot of your solution on one of these little strips. And then depending on the color change, that will tell you what pH value you have. So if I put my solution, I dot my solution here, and I get a green, that means that my pH is probably around 8. Okay, so this is how we can measure in the lab the pH values. Now I want to bring us back to this image that I started this lesson with, which was, hey, we need to know about acids and bases because the human body, actually the organs, have different pH environments. So let's look at that again, now that we understand how to interpret pH values. Okay. This pH here is very, very low. What this means is that our stomach has a very acidic environment, okay, because the pH values are low. And this is going to help us digest our food. Small intestine has a pH of 8.5. Well, it's greater than 7. That means this is going to be basic. Okay. Let's look at our blood. Our blood is 7.4. This is really close to 7. So we consider this value close to neutral. Now you're also going to see that some organs have a wider range of pH values. So this can range anywhere from 5.8 to 7.1. Our urine can range from anywhere that's very acidic to somewhat basic. Okay? And this will depend, these ranges, the reason they're large is because depending on the function, they will have different pH values. So for example, with your saliva, when you are consuming food, oftentimes your saliva becomes more acidic. And that helps you be able to digest your food or be able to break down your food as you eat it. Okay? And then once you're done eating, your pH value in your saliva will increase closer to neutral. Okay, so let's get to it. So in this one, we're going to complete the following table. We're going to classify each solution as an acid, a base, or neutral. Okay. All right, so I am looking at my column header here, and I see I will need to calculate H3O plus concentrations, OH minus concentration. I will need to calculate pH, and then I will have to classify it. So let's start with one of the equations that we will likely use. I'm going to write these in black. Okay, so KW, this is the one that allows me to determine hydroxide and hydronium ion concentrations. So recall KW is equal to 1 times 10 to the negative 14 molar squared, which is equal to H3O plus concentration and OH minus. Okay, that's one of the first equations we're going to use. Now to calculate pH, I will go ahead and do that in green. So for pH, we will use negative log of the hydronium ion concentration. That's one way to use our pH equation. I also showed you a different type of a pH equation where if they give you the pH value and you need to calculate H3O plus concentration, we might need this. So I will provide it here, 10 to the negative pH. So that is just the top equation rearranged. Okay. And then lastly, we're going to need to be able to classify these things. Okay. So I'm going to write that also just in black. So here we're going to classify pH as acidic or basic. So if pH is greater than 7, that's going to be basic. If pH is less than 7, that's going to be acidic. And if it is about 7, it will be neutral. Okay, so let's start with A. So I'm going to call these A, B, and C. Okay. So in A, I'm going to use my KW equation first, okay? Because they have given me my hydronium ion concentration, and I want to calculate the hydroxide. So I'm going to use that KW equation. Okay, so then this will equal the concentration they have given me, which is 5.3 times 10 to the negative third. Remember, all of these are in molar. And then I'm trying to solve for OH minus concentration. So divide both sides by 5.3 times 10 to the negative third, and that will give you OH minus concentration, and that will result in 1.88 times 10 to the negative 12 molar. But you can only have 2 significant digits because that is what the measurement gives you. Okay, so you're limited to 2. So that means 1 and 2. I can only write up to this one. So I look at its neighbor, it's greater than 5. So I need to round up my 8 to 9. So that means here I will have 1.9 times 10 to the negative 12. Okay. That's how many hydroxide ions I will have. That's the concentration of my hydroxide ion. Okay. Now let's calculate pH. So for pH, I know that for pH, that is going to be the negative log of my hydronium concentration. Okay. So here I need to plug in 5.3 times 10 to the negative third. This is going to be in molar. Right. So now here you can put this into your calculator. Make sure you don't forget that negative. And then when you do that, you're going to get pH is equal to 2.2757. Now, how many significant figures can I have? All right, well, I have to look at the total number of significant figures in my concentration measurement, which is 2, the 5 and the 3. So that means I must have 2 digits to the right of my decimal. So that means the 7 is the last digit I need to have for having proper significant digits. So that means I'm going to look at the neighbor. The neighbor is a 5, so I need to round that 7 up to an 8. So this means my pH is 2.28. Well, if my pH is 2.28, that means it is less than 7, so it's going to be acidic. Okay? And that's how you solve that kind of problem. So we're going to repeat the same things for the other ones. It's just figuring out what is your unknown, okay, and then solving for that unknown. Okay, so in B, they have given me hydroxide. I need to calculate the hydronium ion concentration. So I'm going to go ahead and do that in the same way I did the calculation for the hydroxide. So I'm using my KW, and then I have 2.0. And then over here is going to be H3O plus. And that's what I'm solving for. So divide both sides by 2.0 times 10 to the negative 8. And when you do that, you're going to get your hydronium ion concentration. And that should be equal to 5.0 times 10 to the negative 7 molar. So that means our hydronium concentration is 5.0 times 10 to the negative 7 molar. And again, check that your significant digits are correct. I had 2 in my measurement here, so I have 2 in my answer. Okay. So I just calculated hydronium ion concentration. Now they're asking for pH. So let's go ahead and do that pH. pH is always the negative log of the hydronium ion concentration. So now I can look at the hydronium ion concentration here that I just calculated, and I'm going to plug that in. Okay. You cannot plug in here the hydroxide ion concentration. Okay, that's not how we calculate pH. So if you go ahead and plug this into your calculator, you'll see that your pH value is something like this, but we need to check our significant digits. So we look at our concentration. There's 2 significant digits here. That means I need 2 digits to the right of my decimal. Okay, so this is the last digit that I can have. I look at its neighbor. It's only a 1, so that means I'm going to keep it as a 0. Okay, 6.30. This is going to be less than 7. So because it's less than 7, this is considered acidic. Okay. All right, let's do the last one. This one is going to have something that's just a little bit different, but the underlying principles are the same. Okay. Here, I don't have hydronium ion concentration. I don't have the hydroxide. They have given me my pH concentration. Okay. So luckily, with pH concentration, with the pH value, I can plug that pH value into here, and then I can get a hydronium concentration. Okay. So let's go ahead and do that. Let's do it in blue. So this means that if I want to calculate hydronium ion concentrations, because they have given me a pH value, I can just plug that pH value in and do this. Okay. So when I just punch that into my calculator, that means H3O plus 10 to the negative 4.4 is just 3.98 times 10 to the negative 5 molar. Okay. But now let's consider our significant digits. Our pH value has just 1 digit to the right of the decimal. Okay. So what this means is that my concentration value can only have 1 significant digit. So that means this is the last digit I can have. So I'm going to look at its neighbor. Its neighbor is a 9, so that means I will round up the 3 to a 4, and that leaves me with 4 times 10 to the negative 5 molar. Okay. So that is my hydronium ion concentration. Great. Okay. So now let's calculate the last thing that we are missing, which is our hydroxide ion. So here, I'm going to go back to my Kw because I have hydronium ion concentration. I know my Kw because it's a constant. Okay, so I will add the hydronium ion concentration that I just calculated. And I'm going to solve for OH minus, which is what I'm looking for. Okay, so divide both sides by 4 times 10 to the negative 5. That will leave you with OH minus. And when you plug that in, you will get something like this on your calculator. Okay. Now I wrote up to 2 significant digits, but we actually need to fix this because we only have 1 significant digit here in this concentration. So I can only have this one. So I will round it up to 3. So this becomes 3 times 10 to the negative 10 molar. Now my pH was 4.4, which is less than 7. So this must also be acidic. All right, so that is how you use all of the equations that I've introduced in this lesson. That is how you can use them together to find hydronium ions, which then will allow you to find the pH, since you need to input hydronium ions into your to calculate a pH. Okay? And you can calculate hydronium ions if you are given one or the other of these. Okay. All right. So let's talk about neutralization reactions. This is going to be the last topic. So far, we have considered these following reactions. So in lesson 3.1, we looked at adding acid to water, where we looked at an acid compound reacting with water, okay, to produce these products. So here, notice that this is your acid. And because this is donating a proton to water, water is acting as a base because water is accepting that proton. And that's how it's becoming H3O+. We had then also looked at a reaction with base and water. So this was our base because it accepted a proton to become H2, right? And it took that proton from water. So that means this was the acid because water donated a proton, all right? And now it has become OH minus because it lost that proton. So these are the reactions that we've already looked at. But now in a neutralization reaction, we are actually going to react an acid with a base. Okay, so instead of an acid with water or a base with water, we're going to react the acid and the base together. Okay. So specifically, we're going to look at hydroxide bases. What does this mean? It just means that it's a base that has a hydroxide ion in it, an OH. Okay. What is typical about neutralization reactions is that when an acid reacts with a base, you're going to get water and then a salt. This is an ionic compound. Okay. So how does this happen? Well, the hydrogen or the proton from your acid is going to be donated to the hydroxide of your base, and that's how you form water. And then that means that the metal left behind and the anion from the acid left behind are going to come together and they're going to form an ionic compound. So here's an example of that. HCl is an acid because it has a proton to donate. NaOH is a base because it has this hydroxide in it. So the H and the OH will come together to form H2O. And then the NaCl, Na, sodium will bind or will bond with Cl to form a salt. Okay, and you'll notice that the states are all aqueous because this is all being done in the background of water. So you have a beaker with water, then you're adding acid, and then you're adding base and letting everything react. Okay, so let's write a balanced equation for each reaction. All right, so the first thing I need to do is identify my acid and my base. Here is my acid. I know it's an acid because it has this H. This is going to be my base because it has an OH. Okay? So that means the H and the OH will come together to form water. And the state for this is going to be liquid because water is in a liquid state. And then what's left is to pair up the remaining species, which is this K here and this Br. And they're going to form a salt, which is an ionic compound. So whenever you're writing an ionic compound, you have to make sure that you're writing it as a neutral compound. So recall that K will form K plus ions, Br forms Br minus ions. So you only need one of each to make a neutral compound. So I do not need any subscripts. I can just write KBr. And this is going to be aqueous because I'm in an aqueous solution. Okay. Let's do the second one. Oh, also you want to check that your equation is balanced. So you'll notice that I have 2 hydrogens on the right-hand side This is where you would need to add coefficients if it was not balanced. I have 2 hydrogens here, 2 hydrogens on the left-hand side, 1 Br, 1 K, so I'm good there, and 1 oxygen, so everything is balanced. I do not need to add any coefficients. All right, let's do the second one. This is my acid. This is the proton that's going to be donated. So this is acid. I know this is my base. It's a hydroxide base specifically because it has that OH in it. Okay, so that H and that OH will come together to form water. Again, water will always be a product of a neutralization reaction, as well as the salt. What is going to make up my salt? Well, this calcium and this nitrate. Nitrate is a polyatomic ion. Okay? So recall that calcium will form calcium 2 plus in an ionic compound. Nitrate has a minus charge. Okay? So what this means is that if calcium has a 2 plus and nitrate has a 1 negative, I'm going to need 2 nitrate ions in order to cancel out the 2 positive from the calcium. So calcium will have a 2 plus, and then I'm going to need 2 nitrate ions to make a total of a 2 negative so that they will cancel. Okay. All right. Now we need to balance this equation, okay? Because you'll notice that on the right-hand side, I have 2 nitrate ions, right? But on the left-hand side, I only have 1. So what this means is I'm going to, I'm going to add a 2 here in front. So that will balance out my nitrates. Then I have to check that I have enough hydrogens. So I have 2 hydrogens on the left-hand side. So I have 2 hydrogens here, plus another 2 over here. So I have a total of 4 hydrogens. That means I need to add a coefficient. Oh, not a 4, excuse me, a 2. Because 2 times this 2 down here, that gives me 4 hydrogens total on the right-hand side. Now I have 4 hydrogens total on the left-hand side. Okay, now let's check our oxygens. I have 2 oxygens on this side, and I have 2 oxygens on the right-hand side. So that checks out. 1 calcium and 1 calcium. So everything is now balanced. Okay, so this is the very last part. We're going to put it all together in this qualitative way to think about what is happening with acids and bases and how this affects pH. Okay. All right, so here we have 4 different solutions, okay, and we're going to go through each one and thinking about what happens when I have an initial condition and then I add a compound to it. Then I want to know what effect that is going to have on my pH. So let's start with solution A. So initially in my beaker, I have some water and I have some KOH, right? But what is KOH? Well, KOH is an ionic compound. It has a metal and a hydroxide polyatomic ion, right? So when I put this in water, which is what I'm doing here, this will split up into K plus, or it will dissociate into K plus and OH minus. This is also a hydroxide base because it's contributing OH minuses to your solution. So that means that initially you have a basic solution. That potassium hydroxide is making it basic. So now let's add some HCl. Okay, well, what is HCl? Well, the first thing that I notice is that there is a hydrogen here that can be donated as a proton. Okay, this compound can donate a proton. So what this means is that this is an acid. And if it's an acid, that means that this is increasing H3O plus concentrations, okay? Because that's what it's doing. When it donates a proton, it's increasing the H3O plus concentration. So if I started out with a solution that was basic, okay, which means it had a very high pH, and now I'm adding acid to it, that means that my pH is being lowered as I add acid, because a lower pH means something is getting more acidic. Okay? So I'm starting at a high pH with just potassium hydroxide. Then I add hydrochloric acid, and as I add that acid, my pH is going to get lower and lower and lower. Okay. All right, let's look at solution B. I have just water. Well, just water is neutral. Now I'm going to add NaNO3. Let's consider this compound. Well, the first thing I notice is that it's an ionic compound, right? It has a metal, Na, and a non-metal, which is NO3. It's a polyatomic ion. So when I put this in water, which is what I'm doing here, I'm putting it in water, this is going to make Na plus and NO3 minus. Neither of these are going to affect the concentration of hydronium, H3O plus, or hydroxide, OH minus, which is what contributes to acidity and basicity, okay? So because this is not an acid nor a base, that means nothing happens to the pH. The pH is going to stay the same. Okay. I have just added a salt. All right, let's look at solution C. Water, again, I'm just neutral. Now I'm going to add sodium hydroxide. I first notice it's an ionic compound, but then I also notice, so if it's an ionic compound, it's Na plus, OH minus, but then I notice that I have OH minus ions in here, which is what a base is, okay? So a base contributes OH minus to your solution. So what this means is that I started out with a neutral solution. Now I have added a base to it. What that means is that my pH is now getting higher. As I add more and more base, my pH will increase. Okay, let's look at our last solution here. We have water, and then we have KOH. Again, I'm going to notice this is a hydroxide base. This was also present in our solution here in A. Okay. This is a base. It's a hydroxide base. So if it's a base, it must be basic. Now I'm going to add KCl to it. I notice it's an ionic compound, so it will dissociate in water. But I notice that the ions it dissociates into are not going to affect my pH, meaning they're not affecting H3O plus and they're not affecting OH minus. So what this means is that adding KCl is not going to do anything to my pH because KCl is not an acid and it is not a base. Okay. All right. So with that, we have concluded all of the acids and bases, all of the topics in acids and bases lesson. Okay. So here in this one specifically, we looked at how to define Kw of water, and we found that that was this constant here, and that that is equal to the hydronium concentrations and the hydroxide concentration, okay, multiplied. So we learned that. We learned how to calculate pH. There are two forms of the same equation. If you are given H3O plus, you can plug that in there and calculate pH. But if you're given a pH value, you can plug that into here and then calculate hydronium ion concentration. And then lastly, we drew the products of reactants or reactants of neutralization reactions. And the key thing to note here is that in a neutralization reaction, an acid and a base react together, and those two will always form water and salt. Okay. And that will conclude everything for Unit 1.